Hey trigonometry students, today we're going to be going over just some of the fundamentals. Basically these are things that you probably for the most part have gone over in algebra, so this should be mainly review, so we're going to be moving kind of quickly through the material. Having said that, if any point that you find the part confusing, don't be afraid to hit that pause button, regroup, figure out what's going on before proceeding on. So with that said, let's go ahead and get into this. This is from chapter 1 in your book, The Fundamentals. So let's start off with the first bit. A relation maps two different sets together. Okay. Now, a function is a relation that maps a set called a domain to a set called a range. Right? So a function takes a set from domain and maps it over to another set called the range. So basically, if you're given one element in domain, it brings it over to another element in the range. This mapping must have an unambiguous predictive quality. Right, so that means that if I tell you something in the domain, it's not going to possibly mean two or more different things. It means that given any element in the domain, you know exactly what element in the range you're referring to. And so we start off with the first example of this right here. Basically, it's a menu. If I say, how much does a burger cost? Well, according to the menu, it's $5. And if I say, okay, what about chili? How much does chili cost? $5. And how about fries? How much do fries cost? Well, it's going to be $3, right? There's a predictive quality. Now, imagine if I said, okay, I'm buying a burger and that could cost $5 or $3. That would have no predictive quality to it. So we want to make sure that the domain predicts the element that's going to go on in the range. Now note in this example, it doesn't go the other way. If I say I spent $5, you can't tell me what I bought. If I tell you I spent $5, I could have bought a burger, or I could have bought chili, right? It doesn't work in the other direction in this case. It being able to go the other direction becomes important when you're looking at inverse functions, but for just a regular function, we only need the predictive quality to go this direction. Okay. Now this type of function here is a particular type of function. And on to function, right? So basically this means that you've got your basic setup, you know, anything in the domain can go to anything in the range. So what is the domain? It is a burger, chili, and fries. And what's the range? The range is $5 and $3. Alright, so this next function, this is called an one-to-one function. One-to-one. And so we note that the basic quality of the one-to-one function is that everything in the domain goes to only one element in the range, right? So, for instance, this x2 is not going to y1. Right, it's got its own element, so you can almost predict if it's an on-to function. You know, if you have given the y, it works in the other direction almost. Note that just being on-to is not enough for it to have the predictive quality going this direction, because you do have this element here that's mapped nowhere. Okay, so the domain is x1, x2, x3. And then the range is y1, y2, y3, and y4. Alright, so functions that are 1-to-1, but not on 2. We really won't be coming across any of those in this class, but do know that they do exist, particularly if you're doing any kind of programming functions. That's when this comes up a little bit more frequently, but do know that these exist. Very difficult to grab, if not impossible. So let's go ahead and look at the last one. Right here, this function is both a 1-to-1 and on 2. Right? Notice, everything in x goes to 1 and only one element in the y. Right? There are no elements in the domain that go to the same element in the range, and there are no extra elements in the range. So it's 1-to-1 and on 2. And so what is the domain? The domain is 2, 4, and 5. And the range is 1, 3, and 4. Okay. Alright, so this kind of brings us to the vertical line test. If any vertical line intersects the graph of a relation at more than one point anywhere in the graph, then the relation is not a function. So let's take a look at these examples, put this to the test, and we're going to relate it to these guys up here. Alright, so let's take a look. Vertical line test. Now you can, obviously, there's multiple areas where you can draw a vertical line and you'll intercept more than one point. Let's zoom in here. So basically we're saying for this point, we'll call it, at -1. So for -1, that's getting mapped to both this point here. We'll call that 1.75. And it's also getting mapped to -1.75. Right? We have the same element in the domain getting mapped to two different elements in the range. So thus this is not a function. Alright, so let's go ahead and write that in. Not a function. Alright, here, note, it doesn't matter where I draw a vertical line. I'm only going to intercept at most one point on the graph, so this is a function. Alright, here, note that I can draw a vertical line here. Only one point. It passes, but there are these other points where I can draw a vertical line and it does not pass. So, therefore, this is not a function. Alright. So let's go on. Let's use the graph to answer the following. So in this part we're just basically learning how to read a graph. Again, this should be review, but let's just look at it real fast just in case. What is f of -1? Well, you simply go over to where x is -1. Where do you intercept the graph? You intercept it here. And so that looks like that is 1. So f of -1 is 1. What is f of -1 plus f of 2? Well, we already know what -1 is. Or f of -1. That's +1. Now what about f of 2? So we go to 2, come down here, see where we intercept, then go over. We can see clearly that that's going to be a -2. So this is going to be 1 plus -2, and of course that answer is -1. That's how we evaluate that one. Now what about 2 times f of -1? Alright, so f of -1, we already know what that is. So this just becomes 2 times 1, which is 2. Alright, now what about this one? So note, this -2 and +3 are inside the parentheses. So if it's inside the parentheses, we have to evaluate what's inside the parentheses first. This is true for just general functions. This is true for any arithmetic operations. So this becomes simply f of +1. So let's go ahead. We start at +1. where x is positive 1, we go down until we intercept the graph. We can see that that is also going to be negative 2. So this becomes negative 2. Alright, good so far. What is the domain of f? So the domain is simply all the x values. We can see we've got a filled in circle here, a filled in circle here. So we'll be including those points. So the domain of f, we'll use bracket notation, is negative 3, comma, positive 3. Or we can write this in set notation. So we say all real values of x such that x is in between negative 3 and positive 3. And then we close the bracket. Now what about the range? So the range, see we got a filled in circle here, but difference is now we've got a hollow point there. So we're not going to include this point. We write it like this. We say the range is simply, we start with a lower number, negative 2, and it goes up to positive 3. And we make that a bracket to include it. Or in set notation, the range is going to be all real values of y such that we're in between, I'm sorry, it's a little bit lower than negative 2, so that'd be negative 2, we'll call that 0.2, and then the top point's still the same. There we go. So we go from negative 2.2 strictly less than y less than or equal to 3. And that's what the set notation would look like. Alright, good. So let's keep going on. We're going to get into the midpoint formula now. So the midpoint formula is for when you've got two different points right here. So you got a point 1. And we'll say you got another point over here. We'll call this point 2. And you want to know, okay, what is the midpoint in between those two? So if you draw a line in between them, like so, and we're looking for the point that's going to be happening at about the middle. So we'll call the midpoint right there, and that'll be our midpoint. Alright, so how do we find that? So we want to know what is the x coordinate, what is the y coordinate. So note that if we kind of look down here and right there. So what is the midpoint in between these 2 points? This is going to be x1 and x2, because the xy coordinates, this is going to be x1, y1, and this will be x2, y2. Alright, so what is the midpoint between those? So we just simply find the average between these 2 points. So that will simply be, okay, so let's go ahead and kind of map this out. We will see that it'll end up being the average, but let's go look at it this way first. The distance from here to here, well, that's clearly x1. And what is the distance from here to here? That's the distance that we're, one of the distance that we're interested in, because we're going to add this back in. Well, to find this distance right here, we're going to take the far out point, which is x2, subtract the first point, but note that, x2 minus x1, well, that's simply the entire distance. Right, the distance from here to here is x2 minus x1. So we want half that distance. So we're going to to find that, it's going to be divided by 2. Note that we're trying to find the coordinate right here, so we got to add this distance back in. So the midpoint for this guy, I'm going to call it the x bar, equals x1 plus x2 minus x1 divided by 2. Alright, let's do a little arithmetic here. Alright, so we have x2 minus x1 all over 2. Combine these two fractions and you'll end up with x1 plus x2 divided by 2. Note that that is the average of how you would find the average between those 2 points. Add them together, divide it by the number of points. The number of points is 2. Okay, so let's take a look at the other one. It's a slightly different color so you can see it better. Right, here's our y1 point. And there's our y2 point. So we want to find the midpoint for y. We'll note that's just going to be the same way we did the other one. That's y1 plus y2. Divide the whole thing by 2. So the midpoint of x bar y bar equals x2 plus x1 plus x2 divided by 2, y1 plus y2 divided by 2. Okay, there we go. Alright, so that is that. Midpoint comes into play often. You oftentimes want to find center of mass is where this comes into play. Where is the midpoint of an object that you're looking at? So this becomes pretty important in a number of different applications. Let's take a look at the distance formula real fast. So the distance formula, once again, we've got 2 different points. We've got a point here, and then we got another point over here. Alright, let's combine this point like so. Here's P1, P2. P1 has the coordinates x1, y1, and then P2 has the coordinates x2, y2. Alright. So we want to find what is the distance here. We're going to call this one simply d p1 p2. So this is going to be the distance between p1 and p2. Right, and that stands for the length of this line. So let's go ahead and take note of something here. If you bring this line over here across, you bring this line down, what shape do you see popping up here? It's a right triangle. Right, that's the shape that we see. A nice right triangle right there. So right triangle, we can use the Pythagorean's theorem. Right, and if we look at this as this length, this is delta x, and this is delta y, right? So delta x, delta y, a squared plus b squared equals c squared. That's going to be the key to understanding where this is coming from. First off, we got to figure out, okay, well, what is delta x? So in order to do that, let's go ahead and continue this line down, like so, and let's go ahead and bring this down here. Note here we've got the coordinates x1, x2. So we want to know what this distance is right here. And so note that in order to find this distance, all we do is take the distance from the origin here all the way out to there, and we want to subtract out this distance here, which is x1. So delta x is simply x2 minus x1. And so again, this is read as delta x. Generally speaking, almost every time you see a delta in front of a variable like that, it means change in that value. There are exceptions, but generally speaking, that is what you'll experience. Alright, so let's do the same thing for y. We've got, our coordinate y1 right here. And then for y2, let's go ahead and look at it on the axis. This will be our y2. So once again, the way we figure this out is, the length from the origin here all the way up to y2. And what are we looking for? We're looking for this distance right here. That is our delta y. So in order to find delta y, what do we have to do? We have to subtract out this distance here, which is y1. Right? Same as that right there. Alright, so delta y is y2 minus y1. Okay, so let's keep that in mind. Now let's go ahead and apply the Pythagorean's theorem, right? We've got c squared equals a squared plus b squared. Pythagorean's theorem. Now what is c? Well, c is this guy right here, right? What is a? Well, a is delta x. That's that guy right there. What is b? Well, b is delta y. This guy right here. So the Pythagorean theorem. Let's go ahead and we can substitute everything in. Let's go ahead and take the square root of both sides real fast so we can get rid of that square on the left hand side. So we got square root of a squared plus b squared. Right, everything is still staying the same. Of course, now we're going to go ahead and substitute in our values. So this is the distance from P1 to P2 equals the square root of delta x squared plus, a lot of students put a minus in there, it's always a plus, delta y squared. Okay. Alright, so that's basically the formula. Let's go ahead and just write everything all the way out, though. Go ahead and kind of update these highlights for you so you can see it, make sure you see it clearly. Alright, so the distance from P1 to P2 equals, what is delta x? Well, that's this guy here, x2 minus x1. Quantity squared. I'm going to write the square root in just a second, just so that way I don't have to guess at how long I need to make the roof of the square root there. Delta y, that's y2 minus y1, quantity squared. And then let's put that square root on there. There we go. That's the distance formula. Note the distance formula uses a right triangle. We're going to be using right triangles a lot in this course. And then from there we use the Pythagorean theorem to figure out what the distance formula. So you can see that the distance formula is simply an application of the Pythagorean theorem. Now let's go ahead and move on to circles, and we're going to find, surprisingly, that the Pythagorean's theorem, the distance formula, is going to help us understand circles. So it should be a little bit surprising. A circle and a triangle are two very different shapes, but we can use triangles to help us understand circles. And there's going to be a very intricate interplay between those two that we're going to be noticing throughout the vast majority of this semester. Alright, so let's get to this. The equation of a circle. Here we've got a circle that is centered at the origin. And so we want to come up with an equation of the circle. Before we go any further, let's come up with, in words, a definition of a circle. And so how we're gonna define circle is a circle is the collection of all the points that are equidistant from a common point called the center. Alright. What is, they're all equidistant. What is that distance? Well, that's the radius. Alright, so let's go ahead and take a look at this. We're going to zoom in here. Everything is equidistant about that one point. The origin here. So that's our origin, 0, 0. And I'm going to put a random point there. I could have put it here, 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 or anywhere. I'm just putting it there for convenience. Right? So what is that distance right there? That's what we want to know, right? This is our radius. Right? That's what all the points are equidistant about. I can rotate this radius around as much as I want. And it's it's still going to be, it'll still be on the point as long as I start from this origin here. But let's go ahead and look at the coordinates here. Well, this is going to be x. We'll call this a specific point. We're going to call this P naught. And it's got coordinates x naught and y naught. Okay. So what we're going to do is see how this turns into a triangle. Alright, you drop this down. Right there. Well, that's going to be, what is the distance from here to here? Well, that distance is x naught. Alright. And what about this distance right here? What is that going to be? Well, from 0 up to y naught, well, that's simply going to be y naught. Let's apply Pythagorean's theorem. Right? A squared plus b squared equals c squared. Or the distance formula if you would prefer to jump straight to that, but it doesn't matter. X naught. And I'm just going to go ahead and drop the naught part for right now. X squared plus y squared, because that's the b, right? We got an x, there's our x, here's y, there's the y, and then our c right here. Well, that's the same as our radius, so this equals r squared. So there it is. That's the equation of a circle. Right? Note the circle is not a function. The circle is a relation, but it's a very important relation that we're going to be discussing quite a bit. So that's it. That's how you get the equation of a circle. Now let's look at a circle that is not centered about the origin. One that's centered right here. Okay. Now here's where the x naught and y naught are going to come into play. We're going to call the center. Actually, let's go ahead and come back here. Okay. And just kind of drop the knots from the way we're discussing here, just to avoid confusion. The knots are not wrong, but I want to make sure I'm being as consistent as possible from one example to the next. So let's go ahead and come here. And we're going to go ahead and call this center. Let's we'll call this one P naught. So we have X naught and Y naught. And again, we're going to go ahead and pick a point. Doesn't matter where, but we're going to go ahead and select it right here. And we'll just call it point P, and then it's coordinates X and Y. Alright, so we're going to go ahead and say X naught and Y naught are specific values. X and Y are variables, and which means they're, of course, allowed to vary, hence the name variable, as long as the relation is satisfied. Alright, so let's take a look at the distance created here. Alright, so again, we're looking for that distance. What is the length of that distance? That's r, the radius. And you'll notice, when the triangle shape is going to show up again. And so this is our delta x distance. And if you come over here, this is our delta y distance. And so we simply need to apply the distance formula, where the distance is the radius. Right, so the distance between P naught and P equals the radius, which equals square root of x minus x naught, quantity squared, plus y minus y naught, quantity squared. And that's the equation of a circle right there. Now, oftentimes you'll see, instead of x naught and y naught, you'll see h and k. Perfectly acceptable to put it in that way. Note we can rewrite this as r squared, get rid of that square root in there. It's very common to see it written out this way. And you'll see x minus h naught, quantity squared, plus y minus y naught, quantity squared. And this is a very common way to see this written out. Now we can solve this for y as another common way to see it done. So basically we just used a little bit of algebra here. R squared minus x minus h naught, quantity squared, equals y minus y naught squared. And now we take the square root of both sides, positive or negative. R squared minus x minus h naught, quantity squared, equals y minus y naught. So now I just need to add the y naught in there. And I'm sorry, it looks like I kind of mixed my nomenclature. Let's go back to the k naught. Again, it's not going to make a big difference. The meaning is exactly the same, but let's just, to keep it consistent, let's just keep that as k naught. Sorry about that. Add k naught to both sides, and so we have y equals k naught plus or minus the square root of r squared minus x minus h naught squared. And this is again, pretty common way to write it. I want you to notice a few things about this. The equation of a circle, it looks like this. But the k, right, the way that the center is displaced from the origin, you add that displacement here for your k naught. But to move the circle to the right, you have to subtract a number like this, h naught. So that's something that that carries over into function shifts, which again is something that you should have covered in algebra. There'll be a couple of basic homework questions that go over that. That'll remind you of what's going on. This will come into play in a big way as we start getting into the graphs of various trigonometric functions. All right, so that is all I have for the day. I hope this was informative, and I will catch you guys next time.